So hopefully you remember a thing or four about inverses from your Algebra 1 and Algebra 2 days. But in case you don't, well, we're going to talk about the basics also. Okay? So an inverse relation will undo a given relation. Like, what's the inverse relation for plus? Well, it's minus. What's the inverse relation for multiplication? Well, it's division. What's the inverse relation for square rooting? Squaring, right? Squaring and square rooting. Things that undo each other are inverse operations. Okay? So what we're going to do with a relation is we're going to switch your x and your y value. Switch is spelled with a S-W-I-T-C-H. Switch your x and your y values. Okay, so there's three ways we're going to look at this. First is numerically, and then graphically, and then analytically, right? We're going to analyze using our algebra skills. So from a table, right? These were pretty easy back in Algebra 1 when we did them. To find the inverse of a relation, you switch the x and the y. So these are going to become your new y values, right? Or y inverse, right? Look at that notation. That notation is read y inverse, okay, which is different than y. So we're always going to have y inverse. So that's 1, 3, 4, and 6. The x values from your function become the y values for your inverse. And likewise, the y values for your function become the x values of your inverse, right? We're just switching the x's and the y's. Switch the x's and the y's. So now let's do some analysis. The original table is a function. Okay? So in order to decide whether it's a function, we're looking at the x values. Do any of your x values repeat? And the answer is no. We have a 1, a 3, a 4, and a 6 because each x value has exactly one y value. Okay, that's the one-to-one property of a function, that every x value has exactly one y value. However, the inverse is not a function. Okay, look at our new x terms for your inverse, and what do we notice? There is one that has been repeated, right? So we have a repeating x value, which means that it's not a function. Okay, we have a repeated x value. So let's look at our graphs. To find our graphs, you do just like we did. We switch the x and the y values. Okay? So graphically, this means that a function and its inverse will be a reflection over the line y equals x, because we're switching your x and your y coordinates. So it's like we are reflecting, or we're folding our graph along the line y equals x. Okay? So let's do a little table here, and let's plot some points from your graph. So here we have your 5 coordinates, well 5, not your 5, but 5 coordinates from our graph of the function. Here it looks like it's a parabola. Okay, so what we're going to do is we're going to write down all of the inverse coordinates, and then we're going to go back and we're going to plot them. Okay, so here's our notation: A inverse, B inverse, C inverse, D inverse, E inverse. So in order to make an inverse, what do we do to our x's and y's? We switch them. So here is the 5 points that I've now made the inverse of, and I'm going to sketch the graph of. So in other words, this is the graph of a sideways parabola. That's a sideways parabola. So if you notice, even if you don't notice, let me draw in the line y equals x. That's the positive 45-degree line, right, where it goes through every coordinate that is the same. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So this is the y equals x line. So notice every point is directly across from its inverse, right? C is directly across. So it hits your reflection at a 90-degree angle, directly across. Okay, this is true of all inverses. They're directly across from each other on this 45-degree diagonal line. So some vocabulary. If your inverse is also a function, then we call it invertible. An invertible function is one for which we can find an inverse function. Now the key is the word function. So is our blue graph a function? And if it's not, how do we tell? Well, there's something called the vertical line test from algebra. The vertical line test is what we use to see if something is a function. And you simply draw a vertical line through your graph, and we notice how many times it intersects the graph. So how many times does our red vertical line intersect our blue graph? Twice. Right here once and right there twice. That means that the blue graph fails the vertical line test, and it is not a function, or it's not invertible, because the inverse is not a function, right? This graph fails the vertical line test, which means that graph is not the graph of a function. It has two different y values for the same x value, and that makes it not a function. Okay, now let's get to the meat of our problems, and that's the analytical part. So where the first job is really easy, you simply have to switch your x and your y letters in your equation. Okay, to switch the x and the y letters in your equation. And then to solve for y, which eventually we're going to call y inverse, because we want to differentiate it from the y, or the f of x that we're starting with. Okay, so if we have f of x, then we write it as f of x, f inverse of x. So notice all of these have that, so our last step is going to be to change y to function notation. Okay, let's jump right in. Step number 1, switch x and y. Now we have to solve this equation for y. So we want to get y by itself. So first we're going to add 7. Right, let's add 7 to both sides. That means I now have x plus 7 equals 3y. And now I'm going to divide by 3, right? Because I want to get y by itself. So I'm going to divide everything by 3. I don't divide just x. I don't divide just the number. I divide the entire thing. And believe it or not, this is a perfectly happy way to write our answer. X plus 7 divided by 3. Okay? You might see it as 1/3 of x plus 7. Also correct. You might see it as x divided by 3 plus 7 divided by 3. Also correct. All three of those things mean the exact same. So we're just going to leave it as this one, and we write f inverse of x because that's how our problem started. We started with f of x, so we end with f inverse of x, so f minus 1. There we go. Okay, so now here are the trickier ones where we start off with a rational function, which means a fraction. Because we have 2 places to put the y. So everywhere we see an x in our original function, we have to put a y when we create the inverse. Okay, so when we switch x and y, this is what we get. So we have to solve this equation for y, and there are 2 of them. Right? They don't divide each other because they have a -2 and a +3. So we're going to do this algebraically. How do we get rid of a denominator? Well, we multiply by it. So we're going to multiply both sides by y plus 3 in order to get this y out of my denominator. Right? We can't solve for a y in the denominator. So we multiply. You always multiply by the denominator if you want to move it. And we do. We want to move it. So on the left side, we're going to simplify. So we're going to multiply our x into both of those terms. Right? That's what we do when we have parentheses. We simplify by multiplying. So this is x times y plus 3x equals y minus 2. Okay, so that's now a much easier equation to deal with than we had when it was a fraction. So notice how many y's are there? 2 y's. And if we want to solve for y, we need to get the y's on the same side of our equation. So I'm going to move my y by subtracting it. So I'm going to subtract y from the right side to the left side. And at the same time, I'm going to move my 3x to the opposite side. Okay? Because I only want y's on one side and everything else on the other. So not only am I going to subtract my y, I'm going to also subtract 3x. So now it's now a negative 3x on the right side of my equation. And everything else stays like it was. So I have x times y minus y equals minus 3x minus 2. Now, no, you can't just subtract y here. Okay, just like if I had 5x minus x. That's actually okay. But we don't. We have xy, there's a product here, minus y. So we can't just subtract this from that. That is not mathematically legal. So how do we combine our 2 y's into 1 y? And here is your mathematical trick. We have to factor it. Notice that both of these terms have a y in them, right? There's something being multiplied by y. So what if I factor out the y? I change it from a subtraction problem into a multiplication problem. So y divided by y, what's left over? That's just 1x. And if I do y divided by y, what's anything divided by itself? Is 1. So on the left side, I now have x minus 1 times y equals negative 3x minus 2. Okay? That's the key to doing these problems, is to factor out y from both of your terms on the left side. And now it's just a matter of dividing. We're going to divide both sides by x minus 1. Okay, we're going to divide by this to get our y value alone. But we don't want to have y anymore. We started with an f in our problem, so we have to end with f in our answer. And it's f inverse, because this is the inverse equation for the f that we started with, right? It has to be something different when we have manipulated it. Okay, we have one more example of that style, right? We start with a fraction, and our steps are the same. This is x, goes here, and we have 2 places where we put the y. So 2y plus 1 in our numerator and y minus 3 in your denominator. Okay? So we're going to do those same steps to solve this for y and then change it to y inverse. Okay, there's your final answer, right? So this is the key step, is once we get y's on the same side, you factor the y out of each of your terms, right? So we're dividing both of these terms by y, and then we divide the right side by the x minus 2 to get your final inverse function. Very good job. So to tie inverses back into what we were doing last week, compositions, okay? 2 functions are inverses of each other only if, when you do their compositions, right, both ways, when you do f of g of x and g of f of x, and then you reduce, you get x as your answer. Okay, so if you get anything other than x when you are doing your compositions, that means those functions are not inverses of each other. Okay? So to show two functions are inverses, we must show that both equal x. That both compositions. So we have to compose the two functions together, and when you simplify those two compositions, the answer just simplifies to x. Okay? And some of them are going to be pretty obvious, and some of them are going to be much less obvious. So let's do this first one, f of g. Remember what it means to compose? Take this entire equation and plug it in right there. So we're replacing the x value, right, the x variable, in your f function, right, that's the outside one, with your entire equation from g. So this is 2 times a bunch of stuff minus 3. And that bunch of stuff is half of x plus 3 halves. Okay, so there's the composition part. That's where we start. We replace x with an equation from g. So now let's just simplify. What is 2 times 1/2? Well, that's just 1, right? Because 2 divided by 2 is 1. And what is 2 times 3/2? 2 times 3 is 6. 6 divided by 2 is 3, right? So it divides out. And then minus 3, I still have my minus 3 from my original equation. So what's 3 minus 3? 0, and I'm just left with x. Right? That's exactly what we want. If our functions are in fact inverses, the composition will simplify down to just x. So now let's do the other way. Let's take our f and plug it into our g. Okay? So that's 1/2 of a bunch of stuff plus 3 over 2. Okay? And that bunch of stuff happens to be 2x minus 3. So there is your composition. I am putting my f function into my g equation. Now let's simplify. What is 1/2 times 2x? It's just 1x. What's 1/2 times minus 3? Minus 3/2. And then I still have my plus 3/2 for my original equation. Minus 3/2 plus 3/2 is 0. So my answer is just x. So if my functions are inverses of each other, that's exactly what you would expect to happen. Okay? So note, sometimes we use a restricted domain to ensure two functions are inverses of each other. Okay? So I'll be right back. So let's do our two inverses. So let's first do h of k of x. So this is what that composition looks like. So now let's math this out. What is the square root of x plus 10 squared? Right? Those guys undo each other. They're inverse operations, which means I just have x minus 10 left over. So what's x minus 10 plus 10? Well, just x, right? Because these go to 0, which is exactly what we expect for an inverse. So now let's check the opposite way and do h or k of h. So let's simplify. Plus 10 minus 10, well, that's 0. So then what's the square root of x squared? That's just x, because they inverse operate each other. So yes, these are in fact inverses as long as we restrict the domain to only positive values of x. Okay, because that gives you the same graph as root x minus 10. Okay, so there's one thing that I want to mention about number 8, because the inverses are easy to do, but then the math is more complicated. So here I have replaced x with p of x. And let's simplify. So plus 4 minus 4, that's 0. So this is 6 divided by x. Okay? We're going to run into this type of algebra time and time again. So you need to know that instead of dividing by a fraction, we're going to multiply by its reciprocal. And when that happens, 6 divided by 6 is 1, and we just get x as your answer, which is what we expect. Okay? So whenever we divide by a fraction, we stop and instead we multiply by its reciprocal. Okay, very important to remember to do that. So here's our other one, and notice we have that same thing going on here, a number divided by a fraction. So we're going to, instead of dividing by a fraction, we're going to multiply by its reciprocal. So to multiply by x minus 4 divided by 6. Right? So what we notice is the 6's divide out, and that just is x minus 4 plus 4, which also subtract to give you 0, and your answer is just x. Okay? So to form an inverse, you switch the x and the y, and if your two functions compose together to give you x, then those two functions are inverses of each other. Have a swell day.